Hello, this is John Guttak again. It's been a while since you've had the opportunity, or maybe I should say the misfortune, to view a segment recorded by me for 600, but I'm back. I hope it's okay. We spent a fair amount of time this term looking at the role of computation in understanding data. Thinking statistically about data is a relatively new invention dating to about the 17th century. Since its invention in the middle of the 17th century, people have used statistics both to inform and to mislead. Some have willfully used statistics to mislead, others have been merely incompetent, which gets me to the topic of today's lecture. There are three kinds of lies: lies, damned lies, and worst of all, statistics. This quote is often attributed to Mark Twain, but he attributed it to Benjamin Disraeli, and it's probably appropriate that we should attribute it to a politician. And then there's my second most favorite quote about statistics. If you can't prove what you want to prove, demonstrate something else and pretend that they're the same thing. In the days that follows the collision of statistics with the human mind, hardly anyone will notice the difference. In this lecture, we'll list a few ways in which one can be fooled into drawing inappropriate inferences from statistical data. I trust, by the way, that you, as a 600 student, will use this information only for good, i.e. to become a better consumer and purveyor of statistical information, not to be a deceiver. Let's start with the statement that statistical measures do not tell the whole story. In 1973, the statistician F.J. Anscombe published a paper containing this table. It contains the XY coordinates of the points in each of 4 different data sets. I don't expect you to assimilate all of this at a quick glance, so I'm going to provide you with an executive summary to show you that in many ways these 4 data sets are statistically similar. They have the same mean for X and Y in each, the same variance for X and Y, the same correlation between X and Y, and moreover, if we do a linear regression, we'll see that we get the same curve for each of X and Y as depicted here. Does this mean that there's no obvious way to distinguish these data sets from each other? No. One simply needs to plot the data, the actual data, to see that the data sets are not at all alike. So, for example, as we look at this, we can see that this and this don't even resemble each other. And in fact, there's no resemblance between any of the 4 of them. Keep in mind that there are an enormous number of different statistics that can be extracted from any data set. By carefully choosing among these, it's possible to convey a variety of different impressions about the same data. Is it hopeless? No. There's a very simple antidote to this. Look at the data itself. So by plotting the points here, we could see that in fact these data sets were not at all alike. Okay, let's move on to a slightly different topic. Throughout the term, we've emphasized the utility of graphics for quickly conveying information. However, when used carelessly, or worse yet maliciously, a plot can be highly misleading. Consider, for example, this chart depicting housing prices in the United States Middle Western states. This chart suggests that in fact housing prices have been very stable, or were very stable during the period 2006 to 2009. This might cause you to scratch your head. Wait a minute, you might think. Wasn't there a housing crash in 2008? Followed by a global financial crisis? Indeed there was, which raises the question, why don't we see it in this chart? Well, the reason is that I have very cleverly, or perhaps maliciously, chosen a y-axis, which I've displayed logarithmically, and with a very large dynamic range. I've showed housing prices ranging from $10 to $1 million, when in fact, the only interesting part is here. But you really can't see what's going on there because I've made that part intentionally very small. Let's look at another chart that shows exactly the same data. Here I've done the opposite. I've made the dynamic range on the y-axis small, ranging from 185,000 to 220,000, depicted it linearly, therefore exaggerating the changes and making a bad situation look even worse than it was. Let's look at another interesting picture, this one from a journal article. So before I do this, I should ask you to think about your initial and to hope that it's not either a C or a D. Why? Because if it is, you're likely to get a bad grade in this course. Or so might the authors of this article have concluded. And they conclude this in part by looking at this table. You can see here that people whose initials are C or D get considerably lower grades than those lucky people, for example, with an A. Well, not really. Because again, what the authors have done is choose a very small dynamic range here. So in fact, this difference and that difference are not really so large. By the way, the article concluded that students with the initials C or D were more accepting of poor performance and therefore performed more poorly. Of course, one could just have easily concluded that professors don't like students with the initials of C or D and therefore give them bad grades. In fact, in later segments of this lecture, we'll see lots of other reasons to be suspicious of the conclusion in this article.